Section 2.3 is actually the last section of chapter 2, and we're going to be talking about dimension, as you can see there. And I mean, although we have been discussing finite dimensional vector spaces, we really haven't defined the dimension of such an object, right? So the first question is, how should dimensions be defined? Well, before we do define it, we should note that a reasonable definition should force a dimension of Fn to equal n, right? So like of F2, the plane, be two-dimensional, or the line be one-dimensional, right? So we're tempted to define the dimension as the length of a basis. However, a finite dimensional vector space in general has many different bases, right? As we saw from the last lecture. So our attempted definition only makes sense if all the bases in a given vector space have the same length. Fortunately, we have this theorem. Any two bases of a finite dimensional vector space do have the same length. And what's the proof of that? Fairly short. Suppose V is finite dimensional. We're going to let B1 and B2 be two bases of V. Then B1 is linearly independent of V, right? And B2 spans V. So the length of B1 is at most of length B2, right? Because we saw we actually seen this from a theorem. I wish I could remember the section. But in this case, if we have a linearly independent list, B1, and we have B2 that spans V, well then B2, as far as the length goes, is greater than or equal to B1. We can do the same thing by just interchanging the roles. So B2 is at most the length of B1. So what does that imply? Well, that B1 equals the length of B2. Therefore, they do have the same length. So now we can define what a dimension is. Dimension, and I don't know why I'm not underlining this. The dimension, this should be in green, of a finite dimensional vector space is the length of any basis of the vector space. And we denote that as dim V, as it shows here, the dimension of V. So what are examples? The dimension of Fn is equal to n because the standard basis of Fn has length n. So like we said, F2, well that's dimension 2 because the standard basis has length n, right? Length 2. The dimension of p sub m of f is equal to m plus 1 because we have the basis 1 all the way to z to the m that has length m plus 1. Next, we're going to go over a little theorem here. It says if V is finite dimensional and U is a subspace of V, then the dimension of U is less than or equal to that of V. So again, fairly short proof. Suppose V is finite dimensional and U is a subspace of V. Well, then we're going to think of a basis of U as linearly independent less than V, and think of a basis of V as a spanning list in V. Well, now like it says here, from a previous theorem, we can conclude that dimension of U is less than or equal to dimension of V. And here it says from a previous theorem. This is referring to a theorem from section 2.1 that said that the length of a linearly independent list is less than or equal to the length of a spanning list. So that's how we can make that conclusion that the dimension of U is less than or equal to the dimension of V. Okay, so now we have a theorem that says suppose V is finite dimensional. Then every linearly independent list of vectors in V with length that's equal to the dimension of V is a basis of V. And this should make intuitive sense, right? And an easy example people always go with is a standard basis. We can always do that. Kind of just serve that, I guess, that visualization of Euclidean spaces as an example. Although it can be dangerous to only think about Euclidean spaces, not just in this class, but in other classes as well, when we're dealing with metric spaces, topological spaces. We're not dealing with Euclidean spaces all the time. So just careful with that. But again, this should be fairly obvious as far as the intuition goes. And the proof isn't a long one either. So we're going to suppose the dimension of V is equal to n. And these vectors, V1 to Vn, are linearly independent in V. Well, this list can be extended to a basis of V. Right? We had seen in a theorem from the last lecture. However, every basis of V has length n. So in this case, the extension is a trivial one. What does that mean? Well, that no elements are added to this list. In other words, V1 to Vn is already a basis of V, and we have our proof. So, how can we show that the list 5, 7, and 4, 3 is a basis of F2? Well, the list of two vectors in F2 is linearly independent, and the F2 has dimension 2. So this theorem above implies that the linearly independent list of length 2 is a basis of F2. Right, so this theorem, I know some students say, well, this theorem is obvious. Obviously, it's true that this is the case. Which, I mean, it is. But we couldn't use these facts to just show this example that those two vectors are a basis of F2 without showing the necessary proof. And there are more, I shouldn't say complicated examples, but more involved ones, definitely, that you can try. Maybe your professor gives you those to prove or to show. Well, we're going to move on to a theorem that says suppose V is finite dimensional, then every spanning list of vectors in V with length dimension V is a basis of V. And again, this one I guess would be a little less obvious, but not too hard to see. And because of that, it shouldn't have a long proof. So to show this, we're going to suppose that dimension of V is equal to n. And V1 to Vn spans V. Right, well, the list V1 to Vn can be reduced to a basis of V, right, because it spans it, so we can reduce it to a basis. But every basis of V has length n. So in this case, again, just like the reasoning above and the proof, in this case, the reduction is a trivial one, meaning we don't delete any elements from V1 to Vn. So in other words, V1 to Vn is a basis of V. And finally, the question, what is the sum of two subspaces of a finite dimensional vector space. So I guess the question should be more like if we were to add two subspaces to each other, what is the dimension of that new space? And this is this next theorem in the next slide gives a formula for the dimension of sum of two subspaces of a finite dimensional vector space. And this formula is it's analogous to a familiar counting formula, right? The number of elements in the union of two finite sets equals the number of elements in the first set plus the number of elements in the second set minus the number of elements in the intersection. Right, when you might have, actually, let me show you. This can only get your intuition. Sorry, my words without visualizing the formula or the equation can be a bit confusing. So if U1 and U2 are subspaces of a finite dimensional vector space, then the dimension of their sum is equal to a dimension of U1 plus the dimension of U2 minus the dimension of their intersection. That, like I said, that formula should seem a bit familiar from set theory, from basic set theory, how we're counting elements of sets. And as you can see, this proof is quite lengthy. Luckily, this section is so short. This is our last slide. But let's just go through this proof in detail so that we don't get lost. It shouldn't be too hard to follow again, but we do need to be careful. So first things first, we're going to let U1 to UM be a basis of the intersection, U1 with U2. Well, then the dimension of the intersection of U1 and U2 is M, right? Because U1 to UM is a basis, that's length M. Well, because it's a basis of the intersection, it is linearly independent in U1. So this list can be extended to a basis U1 all the way to UM, and then V1 all the way to Vj of U1. Right? Now it's a basis of U1. So we extended this linearly independent list in U1, we extended it to a basis. And how are we allowed to do that? Well, we saw that theorem that allows that from the previous lecture. Well, now the dimension of U1 is equal to M plus J, right? Where do we get the J from? Well, from V1 to Vj. That's list of length J. So the dimension of U1 is equal to M plus J. Also, extend U1 to UM to a basis, where it's U1 to UM, and then including W1 to WK, so it's a basis of U2, right? We're doing the same thing, but now with U2. Well, then the dimension of U2 is M plus K. And again, M came from the length of this list, and K came from the length of these this list, W's. So now we're going to show that U1 to UM, that list including V1 to Vj, and also including W1 to WK, is a basis of U1 plus U2. And well, as it says here, it'll complete the proof because we'll have that the dimension of U1 plus U2 is equal to M plus J plus K, which is equal to M plus J plus M plus K minus M. Right, so now that's just the same thing as dimension of U1 plus dimension of U2 minus the dimension of their intersection. So clearly the span of all these vectors of this list here contains U1 and U2, right? So it's equal to U1 plus U2. So to show that this list is a basis of U1 plus U2, we only need to show that it is linearly independent, right? Because these vectors already span U1 plus U2. But if they're linearly independent, well, then they're a basis of U1 plus U2. So we're going to suppose that this long linear combination of all these vectors is equal to 0, where all A, B's, and C's are scalar, right? Just as we would show that any vectors are linearly independent. We're going to set it equal to 0 and see if we can get the implication or the result that all the scalars are 0 or have to be 0. Oh, well, that's just what I said. So the equation above, this equation here, which I don't want to say because it would take me a good half hour, it can be rewritten as this form. So just a little algebra, we move all the AU's and BV's to one side or to the other side. And what does that show? Well, that C1, the linear combination C1 times W1 plus all the way to CK times WK, that linear combination, or the linear combination of that form, is in U1. All the W's are in U2, so it implies that that linear combination is in the intersection of U1 and U2. So because U1 to UM is a basis of the intersection, well, we can write C1, or actually, well, I'm not even going to say it, this linear combination equal to this linear combination for some choice of scalars D1 to Dn. Right, and that's because, well, this is in the intersection, and as it says here, this was a basis, so we can get this equation down here. But U1 to UM and W1 to WK is linearly independent. Right? So, if you don't remember that, I'm going to put it in red. It was a basis of U2. So that last equation implies that, or this is what it's referring to, this last equation implies that all C's and D's are 0. So we don't need to worry about the W's now, because actually, before I even go over this line, let me just erase all these marks to not confuse us. Well, this here, our original equation, this is what it's talking about. This equation can now be reduced to this, because we don't have to worry about the W's anymore. And now, because U1 to UM and V1 to Vj, that whole list is linearly independent, it also implies that all the A's and B's are equal to 0. Therefore, all the A, B's, and C's are equal to 0, which concludes the proof. So it's not too hard to follow. Maybe it'll help if you draw the Venn diagram and then show that U1 to UM and everything in between spans the intersection. Over here, that if we call this one U1, U2, U1 dot 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 UM, W1 dot 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 WK as a basis for U2. Same thing for, I'm just going to write it like this, U's and V's spans are as a basis of U1, and you can kind of see the reasoning there. But I know it's a long proof, but it shouldn't be too hard to follow. As professors usually recommend, try to write the proof on your own to get the intuition wherever you get stuck. That's where you kind of see what not necessarily even clever thing the proof did or the person who proved this did, but just kind of see what direction they go, what's the reasoning they use, and see if you can follow it through so that we can have this important theorem in our toolbox, so to speak.